What's up, guys? Let's talk about latency and throughput. So, let's learn about the basic characteristics of a network that help to meet latency and throughput goals. We often use high level abstractions like sockets, message passing, remote procedure calls, or even more advanced constructs through API calls to simplify the complexities involved in network communications. Applications have different needs in terms of user perceived latency and throughput. For example, say we have a max budget of 500 milliseconds for an API call. A call needs to traverse across countries. The network takes about 150 to 250 milliseconds of that 500 milliseconds, leaving only 250 milliseconds for the actual processing on the server side and the client side. So, knowing what our latency is caused by helps us write a better service level agreement and possible ways to reduce latency. If multiple round trips are required to send data, this can add user perceived latency, but if we can do this in parallel, this will cut down our costs. For example, name resolution with DNS can incur latency if the name resolution isn't already cached. So there are four important characteristics about the network that we'll discuss. For example, throughput, latency, jitter, latency bandwidth product. And we'll classify applications based on delay so we can build an API that meets our needs. So throughput is the process to process logical data rate that inevitably passes through many network hops. If we have a 1 megabit per second effective throughput of some link or network, we can't send more than 1 megabit of data in a second. We're going to need to send the remaining data in the next second. The amount of data that can be transmitted from the sender to the receiver is measured by throughput. So if an IoT device can only process 1 megabit per second and the network can provide 2 megabits per second, then the IoT device is not fully utilizing the network. So let's talk about latency. Latency means how long in terms of time a user level message takes to travel from the sender to the receiver. Often more concerned about the user perceived delay, which is a function of the round trip time. So throughput and latency have trade-offs. Increasing the throughput might increase the latency as well. And network latency is built up of the following components: the transmission delay, the propagation delay, the queuing delay, and the node processing delay, which we'll get into. So let's talk about the transmission delay. The time it takes to place a packet on the transmission link is the transmission delay, and we can calculate the delay with the formula packet size over bandwidth. So the size of the packet affects the delay. The transmission delay is inversely correlated with the bandwidth, so the higher your bandwidth, the less time it'll take to place a packet on the transmission link. And if you compress data over the network, it'll help reduce this delay. Propagation delay is the time a bit takes to go from start host to end host. For example, in the case of cross-continental links, the propagation delay would be large because bits need to travel from one continent to another. And you can calculate the propagation delay using the following formula. So distance over speed. Distance is directly proportional and speed is inversely proportional to the propagation delay. So for example, the Mars rover, Earth to Mars is about 134 million kilometers. Commands to it take about 7.4 minutes to reach, and this is assuming that the data will propagate at the speed of light. Operators can't maneuver the rover in real time from Earth, so they rely on autonomous capabilities of the rover and report the results back to Earth. So, for example, content caches like content delivery networks, CDNs, they're targeting propagation delay. And just to note, for a specific copper wire, information can flow at 2/3 the speed of light. So, queuing delay is the time needed for a node to hold the packet before it can proceed. A packet is kept in a queue until its turn comes up, and a network packet needs to relay through many network routers to reach the final destination. A packet might need to wait in a queue at a router before it can proceed, just like a traffic intersection. Queuing delays depend on multiple factors, like the time interval between packets, transmission capacity of the outgoing link, the current congestion conditions at the router, and processing delay is the time the node, the routers, and the end host, the server, take to process the packet. It depends on the processing speed of the nodes and the end host. So, variation in latency is called jitter. This is the measure of how latency changes from one packet to the next. 3 packets are transmitted with an equal delay between them, but only one of them gets delayed, and this delay is measured by the jitter. Jitter is usually measured in milliseconds. And so, if you open up your terminal and you put in this command, it'll give us like a time sequence that has these numbers, maybe, right? This is the delay. And due to queuing delays, changes in the route, etc., like these numbers can change, right? And if you want to calculate the absolute differences between them given to the right, and then if you take the mean of all the delays differences, you'll get the jitter, right? And usually networks with lower jitter are considered better than ones with bigger jitter over time. So if you look at, say these are our delays, right? And you look at the differences between them, so you get 0.7, and then you get 0, 0, and 0.1, and then you take the mean of all these, you'll get our jitter, which is 0.2 milliseconds. So sending one packet and then waiting for a response is wasteful. So back-to-back transmissions will increase the network utilization. So how many packets can a link hold? We can determine this using the latency bandwidth product. This is the amount of time that could be in transit through the network at any time. So this is latency times bandwidth. And for example, effective bandwidth measured on the client side is 1 megabit per second. Client to service user perceived time is 200 milliseconds. So we just need to multiply these two together and we'll get 200 kilobits. And we aren't fully utilizing the network if we don't send all the data that a link can hold. So modern network applications are built using APIs, and by understanding the delay needs of the applications, we can design the right APIs. Different applications have different requirements. So for some applications, we want to fetch a web page that has text and images. And then some applications, we want to stream recorded audio and video. Some applications, we want to stream live events like video, audio. In this case, we want to have an upper limit of 300 milliseconds, and 100 milliseconds is considered really good. And we also want to have an application that can facilitate interactive bidirectional communication, right? So we can divide these applications into different classes based off of delay, such as elastic and real-time applications. So elastic applications can tolerate the delay. So emails, we can deliver it to a recipient with some delay. It doesn't really matter if there's, more or less delay. Eventually, if they get it, then it's a pretty good application, right? And then we have real-time applications that can't tolerate substantial delay, like space shuttle navigation systems, right? We can't afford any delay in these type of systems. And then there are elastic applications, like interactive, any application that allows us to input data and get a response, for example, Telnet. Interactive bulk, any application that allows us to input data and get a large amount of responses, for example, file transfer protocol. Asynchronous applications, any application that doesn't wait for the response to give the next instruction, for example, email. And then we have real-time applications. And here we have hard intolerant applications, and this doesn't allow any tolerance for the delay, right? And for example, live video conferencing. Then we have soft and tolerant applications, which means they're a little bit more tolerant to delay. For example, web browsing. Then in soft applications, or soft or tolerant applications, we have adaptive applications, which adjust their functionality according to the network conditions. For example, the playback point of a live streaming event. And then we have non-adaptive applications, which applications that don't adjust their functionality to network conditions. Playback time is, for example, playback time is 300 milliseconds and suddenly packets are arriving within 100 milliseconds. The packets will still have to wait for 300 milliseconds before they're played back. So, types of real-time applications. There's one more class of adaptive real-time applications, which are rate adaptive. And this depends on prevailing network conditions measured by delay, jitter, or some quality of experience metric. Application changes the quality of the video according to network conditions. YouTube has different options for video quality, for example, and if the bandwidth is large, then the quality of the video increases. And in summary, now we know how a typical network behaves and where to look when latency or throughput is not up to our liking or needs. If an API takes too long, we need to find out its constituent latency component to see which component is giving high latency. So let's do a quiz. So number 1, by increasing the bandwidth of a link, which delay decreases? So we know propagation delay is like how much distance there is, like between Earth and Mars, right? The propagation delay would be huge, right? And then queuing delay we know is like a traffic intersection, right? This is the amount of time a node or a packet has to wait on the node before being transmitted. And we also know that processing delay is the amount of time spent processing the packet by either the client or the server, right? And that leaves us with C, the transmission delay. So this is the amount of time it takes for a packet to get on the transmission link. If we increase the bandwidth of our transmission link, right, then that allows us to put more packets on the transmission link faster, right? So the answer is C. Let's assume we have a bandwidth of 200 megabits per second and a latency is 30 seconds. How many megabits does the network hold on the link? How much does it hold on that link? So this is obviously our latency bandwidth product, and we just need to do 2 megabits per second times and our latency. So we have our bandwidth times our latency, and we want to do round trip time. So we need to multiply this by 2. So that gives us 2 times 60, which equals 120 something, right? I think this is megabits per second something, right? some unit, and this is in bits, right? So we want to divide it by 8, and that'll give us 15 something. So this will give us 15 bytes, right? So this will be 15 megabytes. You can do the math yourself, but it'll be D, right? And which is an example of an intolerant real-time application. So streaming audio, we can always just wait for it to buffer. A video game, it's okay if there's some lag. But C, robotic surgery. This is definitely intolerant. If there's any delay, someone could die. So the answer is C, right? By decreasing the distance between end-to-end devices, which delay decreases? Well, this is very similar to a CDN, right? And CDNs tackle propagation delay. So the answer is B. So I hope you learned something. Hopefully you enjoyed this. Leave a like, comment, subscribe. Let me know if I should change anything in the way I'm presenting this or talking about it. Thanks for watching.